Hello everyone, welcome back to our NASA Earth Exchange workshop series. So today I'm going to talk about how to accessing LOCA data on OpenNEX platforms. This is my outline. So first, what is LOCA data anyway, right? And second is just how to actually access this on OpenNEX. What I mean is actually Amazon Web Services, basically commercial cloud. The third, I'm going to give you a hands-on example on how to analyze climate extremes of New York City in the future. All right? Okay, so this slide was from my talk previous time. I talked about we actually generated 4 downscale data sets on NEX. And LOCA is one of them. So you might be actually interested to ask why LOCA is so different, or so everybody is interested in this data set. Well, I have to say I'm not the expert of LOCA. LOCA is actually developed by Dave Pierce at Scripps. So I happen to just get his picture. So this is from his website. Actually, you can go to loca.ucsd.edu. So I actually borrowed some of his slides here, so I'm going to give you some very, very basic introduction, but I really encourage you to visit his website and learn a little bit more. So this is a very typical downscaling system. So last time we talked about how to do bias correction. But there's a different or second step in statistical downscaling, which is how do you actually really downscale or interpolate, coarse resolution GCM output to higher resolution, grids. So there are different ways you can do it. This called constructed analogues, which is a traditional way you can to do the spatial downscaling. As you can tell, well, to learn LOCA, we have to learn constructed analogues first. All right. So let's see. This is what we have done bias correction. So this is a bias corrected GCM output, which is coarse resolution from the future. Now you want to actually try to find an analog or example of similar the weather maps, which is from the history. So basically you can use analogs or just examples from the history to emulate in the future, right? So you go back and search all those records and find some similar to what predict in the future. Now, because it's so extremely difficult to find a perfect match. So most of the time, you're going to actually find multiple, or even tens or 30. Actually, we use the third in BCCA. Anyway, so yeah, you're going to have multiple of those matches, and none of them are perfect match. So you're trying to actually assign some different weight to those different samples. So when you add them together, you actually get better results. To emulate or to emulate the future scenario. So that's basically what the construct analogs does. Take the GCM output, go search in history records, and take the records and do some sort of weighting, and then you get a match for the future. And once those are coarse resolution, right? But once you have those analogs from the historical period, you can actually use the same dates, but now you actually use the fine resolution maps, and then also apply the same weight, and you get the higher resolution climate map for the future, which is what we need, or downscaled climate maps. Now, from what we have just described, you probably already noticed there's some issue, right? Because we used weighted sum or average, it's basically average or some regression. It's average of past climate. that means some spatial details or features get smoothed out. So a second one is, maybe I can go to the next stage. All right. So this is the GCM. And in order to simulate this one, we're going back to the historical records and pick someone very similar and average them to get the downscaled. The problem is, once you actually average them, there are some features where not in the GCM will actually appear. So, because those are not perfect match, right? Remember we said that. So, in a sense, this is especially for precipitation, you're going to actually get some very, very small precipitation or drizzling somewhere else, not predicted by the GCM, but will appear in your downscaled the data set. So that's actually another problem. So in order to solve these problems with construct analogs, Dave Pierce actually came up with this idea. It's kind of interesting, and it's not complicated to understand. So first, instead of just using the analogs for the whole domain, say for whole US, we actually going to define or search some kind of regions. For let's say for this one is the Southwest US. You don't have to use use Northwest US to match with the somewhere here, right? So basically, you use some regional patterns to match, to search for the analogs in the historical record. Second, now, instead of just averaging those analogs, we're actually going to find the best one, just one, for each pixels that actually from those regional analogs. So we're going to do this pixel by pixel. Of course, now, because we're going to pick the each pixel from the analogs, there's some point you're going to choose the pixel from different analogs, right? That's fine. So that's actually define what is Dave Pierce called the edges. So it's only on those edges you have the values from different analogs. So, but it's only like 30% of the points now also are edge points. So we don't have to average every point for all the analogs. So it's a reduce of those points for average. And of course, the area, because it's usually edge, it's much, much smaller, right? So basically, you do all this processing, you get what he called, greatly reduced average means. So you have better extremes because you don't actually smooth out, daily precipitation. You have better spatial coherence. What it means is actually you actually have local effect, not like you have rainfall somewhere that's in San Jose and you get the whole rain drizzling over Northern California. So, and of course, you have less drizzle problem. So this is the advantages of LOCA. Of course, you have to pay some cost, right, to get this data set. The main challenge of LOCA is it needs more computing resources to process data because it's take more steps and you have to do this pixel by pixel. So you need something like NEX to process the whole data set. That's the cost, the price we pay to generate this data set. But anyway, we're able to do that. So this is the paper from 2014, the original LOCA paper on the Journal of Hydrometeorology. So I really, this is actually a very interesting paper, and there's some very interesting technical details in this paper. So if you want, I encourage you to read the paper. Dave Pierce is actually a very good scientist, and then he's also he has a very strong technical background. There's some actually algorithm in that paper is really interesting. Yeah, at least interesting to me. So I think, yeah, if you read the paper, you can learn something new. All right. So this is about, very brief introduction of LOCA.